welcome to this problem walkthrough. Today, we'll be exploring problem number 2158, amount of new area painted each day. In this session, we'll break down the problem, analyze different approaches, and work towards an optimal solution. Let's dive in. In this problem, you are tasked with calculating the amount of new area painted each day based on a series of intervals. You are given a 2D array called paint, where each entry paint, I, specifies the range of indices to be painted on the ith day. The range is inclusive at the start and exclusive at the end, so the interval, start_I, end_I, means painting from start_I to end_I1. The key detail here is that if an interval overlaps with areas that were already painted on previous days, that overlapping section should not be counted as newly painted for the current day. Your task is to return an array result, where each element represents the amount of new area painted on the corresponding day. We'll also need to consider the constraints carefully, ensuring the solution is efficient for up to 100,000 days of painting. Let's look at an example to clarify the problem. Suppose the input paint array is 1, 4, 4, 7, 5, 8. On day 1, we paint the interval 1, 4, which is entirely new, so the result for day 1 is 3. On day 2, we paint the interval 4, 7, which is also entirely new, giving us 3 more units for day 2. On day 3, we paint the interval 5, 8, but this overlaps with the area 5, 7, which was already painted on previous days. Only the section 7, 8 is new, so the result for day 3 is 1. The final output is 3, 3, 1. This example demonstrates how overlapping areas are excluded when calculating the new area for each day. Here's another example for illustration. If the input is paint equals 1, 5, 2, 4, on day 1 we paint the interval 1, 5, which is completely new, so the result for day 1 is 4. On day 2, we attempt to paint the interval 2, 4, but this range is already fully covered by the area painted on day 1. Since there's no new area being painted, the result for day 2 is 0. The final output in this case is 4, 0. This example highlights how intervals that are completely covered by previous days contribute 0 to the result. Let's consider one final example. If the input paint array is 1, 4, 2, 5, 3, 6, on day 1 we paint the interval 1, 4, which is entirely new, resulting in 3 units for day 1. On day 2, we paint the interval 2, 5, but the section 2, 4 is already covered, leaving only 4, 5 is new, so the result for day 2 is 2. On day 3, we paint the interval 3, 6, but the sections 3, 5 are already covered, leaving only 5, 6 as new, so the result for day 3 is 1. The output for this example is 3, 2, 1. The problem also comes with constraints, such as limiting the input size to ensure efficiency. It's important to handle cases like fully overlapping intervals, disjoint intervals, and scenarios near the boundaries of the allowed range efficiently. By breaking the problem into these components, we can design an effective solution that meets the requirements. To solve this problem, one straightforward approach we can consider is the brute force method. The intuition here is to simulate the painting process day by day. For each interval in the given paint array, we iterate over the range it represents and track which sections of the wall have been painted. This can be done using a Boolean array called painted, where each index corresponds to whether that section has been painted or not. Each day, as we process the interval, we count how many previously unpainted sections are painted for the first time and add that count to our result. While this method is simple and intuitive, it has significant limitations. The time complexity is O, n*m, where n is the number of intervals and m is the length of the largest interval. For a large number of intervals or wide ranges, this approach quickly becomes inefficient due to repeated iterations over the same sections. Additionally, the space complexity is proportional to the maximum endpoint in the paint array, which can also grow significantly. These inefficiencies make the brute force approach unsuitable for large inputs. To address the inefficiencies of the brute force approach, we can use an optimized method based on the sweepline technique. The key idea here is to reduce redundant checks and avoid iterating over the same sections multiple times. Instead of simulating each interval fully, we use 2 auxiliary arrays, painted and last_painted. The painted array tracks the farthest index that has been painted at each section, while last_painted keeps track of the last index where new painting stopped. To process each interval, we start with a pointer at the beginning of the range and move through it only as long as we encounter unpainted sections. As we go, we update the painted array to mark the furthest point reached and increment a counter to keep track of how many new sections are painted. By ensuring we only process unpainted sections, this approach avoids redundant iterations and minimizes wasted computation. The optimized sweep line technique significantly improves the efficiency of our solution. Its time complexity is O, n plus k, where n is the number of intervals and k is the total number of positions painted. This is far better than the O, n asterisk m, time complexity of the brute force approach, especially for larger inputs. The space complexity of this method is O, max_end, as we maintain auxiliary arrays proportional to the maximum endpoint in the paint array. These improvements make the sweep line method highly scalable. By reducing redundant checks and processing each segment only when necessary, the sweep line approach ensures that we can handle a greater number of intervals and larger ranges efficiently. After evaluating both approaches, we chose the optimized sweep line technique for its balance of efficiency and scalability. While the brute force method is simpler to implement, its O, n asterisk m, time complexity makes it impractical for competitive programming scenarios with larger inputs. In contrast, the sweep line approach, with its O, n plus k, complexity, ensures that each segment is processed only once, significantly reducing the computational burden. The use of auxiliary arrays like painted and last_painted also makes it easier to manage overlapping intervals while maintaining correctness. Although the sweep line method requires additional memory, this trade-off is acceptable given the substantial reduction in runtime. Overall, the sweep line approach is a clear winner for this problem, offering a robust solution that is well suited for both accuracy and speed. To solve this problem, we need to calculate how much new area gets painted each day, given a series of intervals where painting occurs. Each interval specifies a start and end point, and our goal is to determine the contribution of newly painted sections for each day. To do this, we start by initializing two key data structures. First, we use an array called painted, where each index corresponds to a unit length along the line. This array will help us keep track of which sections have already been painted. Second, we create a list called new_paint that will store the amount of newly painted area for each interval. This structure is sized based on the number of intervals provided as input. The painted array acts as a persistent record, ensuring we can check and update painted sections efficiently, while the new_paint list directly corresponds to the problem's required output. With these in place, we can simulate the painting process step by step for each interval. Now, for each interval, start_I, end_I, in the input, we simulate the painting process in 3 stages. First, we iterate over the range defined by the interval. For each unit j from start_I to end_I1, we check whether the section of the line at j has already been painted. If it hasn't, indicated by painted, j equals 0, we mark it as painted by setting painted, j equals 1. At the same time, we increment a counter called newly_painted to track how many sections are newly painted during this interval. Once the iteration is complete for the current interval, we append the value of newly_painted to the new_paint list. This ensures that each interval's contribution to the newly painted area is recorded. After processing all intervals, we simply return the new_paint list as the final result. By using the painted array to avoid double counting in the new_paint list to store results incrementally, this approach effectively handles overlapping intervals and ensures accuracy. To better understand the algorithm, let's examine the data structures and their roles. The painted array is central to tracking which sections of the line have been painted. Its size is determined by the range of intervals in the input, which allows us to track each unit of the line with precision. This array enables constant time checking and updating, which is crucial for efficiency. The new_paint list, on the other hand, directly corresponds to the result. It stores the amount of newly painted area for each interval, with its size equal to the number of intervals. In terms of complexity, processing each interval, start_I, end_I, involves iterating through its range, resulting in a time complexity of O, L, where L is the total length of all intervals combined. The space complexity is O, M, for the painted array, where m is the maximum range of the intervals, and o, n, for the new underscore paint list, where n is the number of intervals. While this brute force approach is straightforward, it can be optimized using advanced techniques like segment trees or sweepline algorithms to reduce redundant operations. These methods, however, introduce additional implementation complexity. Let's walk through an example to see the algorithm in action. Suppose the input is paint equals 1, 4, 2, 5, 7, 8. On day 1, we paint the interval 1, 4. This results in 3 newly painted sections, and the painted array becomes 0, 1, 1, 1, 0, 0, 0, 0. On day 2, we process the interval 2, 5. Of these sections, only section 4 is unpainted, so the newly painted area is 1. The painted array updates to 0, 1, 1, 1, 1, 0, 0, 0. Finally, on day 3, we handle the interval 7, 8. Since section 7 is unpainted, the newly painted area is 1, and the painted array becomes 0, 1, 1, 1, 1, 0, 0, 1. The resulting new underscore paint list is 3, 1, 1, which represents the amount of new area painted on each day. This example illustrates how the algorithm tracks and updates the painted sections while calculating the newly painted area efficiently for each interval. This implementation begins by determining the maximum endpoint across all the intervals provided in the paint list. The painted array is initialized to a size that accommodates this maximum endpoint, with all elements set to 0, representing unpainted sections. The result list is prepared to store the new area painted for each day's interval. The algorithm iterates through each interval, start, end, in the input. For every unit within the interval, it checks whether that unit has already been painted by examining the corresponding index in the painted array. If the unit is unpainted, value is 0, it marks it as painted, sets the value to 1, and increments the new underscore paint counter. This counter accumulates the total new area painted for the current interval. After processing the interval, the new underscore paint count is appended to the result list. Once all intervals are processed, the result list, which contains the new area painted for each day, is returned as the output. This approach ensures that each unit of the range is checked and painted only once, leading to an efficient calculation of the new painted areas. It handles edge cases, such as overlapping intervals, by checking and marking individual units incrementally. Here, we begin by importing the necessary utility classes and defining our solution class. The method amountPainted takes a 2D array paint, where each subarray represents the start and end of an interval for a day's painting. Our first task is to determine the maximum endpoint among all intervals. This helps us initialize a sufficiently large array to track which sections of the area have been painted. We iterate through the paint array, comparing each interval's endpoint to update max endpoint. Once we have the maximum endpoint, we create an array called painted to keep track of the painted sections, initializing it to fit the entire range of possible positions. We also define a result array to store the amount of new area painted for each day. Next, we process each interval in the paint array. For each day, we extract the start and end points of the interval and initialize a counter, new paint, to track the area newly painted for that day. We then iterate through the range defined by start and end. For each position, if it hasn't been painted yet, we mark it as painted by setting the corresponding index in the painted array to 1. At the same time, we increment the new paint counter. After processing the interval, we store the value of new paint in the result array for that day. Finally, once all intervals have been processed, we return the result array, which contains the amount of newly painted area for each day. We're starting with a simple example where the input intervals are 1, 4, 4, 7, 5, 8. First, we initialize by determining the maximum endpoint across all intervals, which is 8, and create a painted list of size 9, initialized to zeros. This list helps us track which indices have already been painted. We also initialize an empty result list to store the amount of new area painted for each interval. Now, let's process the first interval, 1, 4. We initialize new underscore paint to 0 and iterate from 1 to 3. At each step, if the current index hasn't been painted yet, we mark it as painted in the painted list and increment new underscore paint. For indices 1, 2, and 3, all were initially unpainted, so we updated painted and increment new underscore paint accordingly. By the end of this interval, new_paint equals 3, which we append to the result list, making result equals 3 so far. Next, we move to the second interval, 4, 7. Again, we initialize new_paint to 0 and iterate from index 4 to 6. For index 4, it is unpainted, so we mark it as painted and increase new_paint to 1. Similarly, indices 5 and 6 are also unpainted, so we mark them and increment new_paint to 2 and then 3. At the end of this interval, we append new_paint, which is 3, to our result, making it 3, 3. Now, let's process the third interval, 5, 8. As usual, we start with new_paint set to 0 and iterate from index 5 to 7. However, indices 5 and 6 are already painted, so we skip them. Index 7 is unpainted, so we mark it as painted and increment new_paint to 1. After processing this interval, we append new_paint to result, resulting in a final output of 3, 3, 1. Now, let's look at another example with overlapping intervals 0, 2, 1, 4, 2, 5. We begin by initializing the variables. The max_endpoint is 5, so we create a painted list of size 6 filled with zeros and an empty result list. For the first interval, 0, 2, we initialize new_paint to 0 and iterate over indices 0 and 1. Both are unpainted, so we mark them as painted and increment new_paint to 2. At the end of this interval, we append new_paint to result, making it 2. Next, we process the second interval, 1, 4. Starting with new_paint at 0, we iterate through indices 1, 2, and 3. Index 1 is already painted, so we skip it. Index 2 is unpainted, so we mark it as painted and increment new_paint to 1. Similarly, index 3 is unpainted, so we mark it and increment new_paint to 2. At the end of this interval, we append new_paint to result, making it 2, 2. Finally, for the third interval, 2, 5, we iterate over indices 2, 3, and 4. Indices 2 and 3 are already painted, so we skip them. Index 4 is unpainted, so we mark it as painted and increment new_paint to 1. After appending new_paint to result, the final output for this example is 2, 2, 1. Let's now consider a case with non-overlapping intervals 0, 2, 3, 5, 6, 8. We initialize max_endpoint as 8, create a painted list of size 9 initialized to zeros, and start with an empty result list. For the first interval, 0, 2, we set new_paint to 0 and iterate through indices 0 and 1. Both are unpainted, so we mark them as painted and increment new_paint to 2. Appending new_paint to result gives 2 so far. Next, we handle the second interval, 3, 5. Again, we start with new_paint as 0 and iterate through indices 3 and 4. Both indices are unpainted, so we mark them as painted and increment new_paint to 2. Appending this value to result gives 2, 2. Finally, for the third interval, 6, 8, we iterate through indices 6 and 7. Both are unpainted, so we mark them as painted and increment new_paint to 2. After appending this value, the final result for this example is 2, 2, 2. To analyze the time complexity of the solution, we need to consider two main operations. First, calculating the maximum endpoint among all intervals. This is done using a single iteration over the list of intervals, where we extract the endpoint for each interval and find the maximum value. Since this involves processing each interval once, and there are n intervals, this step runs in O(n) time. The second operation involves painting the intervals. For each interval, we iterate through its range, marking the corresponding positions in the painted array. If an interval spans from start to end, the inner loop performs end-start iterations. In the worst case, if we sum up all iterations across all intervals, the total work done is proportional to the combined length of all intervals. This means the second step takes O(L) time, where L is the total length of the union of all intervals. Now, combining these two steps, the overall time complexity of the solution is O(n) plus L. In the best case scenario, where the intervals are disjoint and their total length L is small, the time complexity reduces to O(n). For the space complexity, the most significant factor is the painted array, which has a size based on the maximum endpoint value. If the maximum endpoint is m, the array requires m space. Additionally, we store the result of new areas painted for each interval in a list, which has a size of n. Temporary variables like new_paint, start, and end require constant space, which is 1. When we combine these factors, the total space complexity of the solution is m plus n. When comparing this approach to a brute force solution, the difference in efficiency becomes clear. A naive approach might involve maintaining a 2D grid or repeatedly checking overlaps for each interval, leading to a time complexity of n squared, or worse due to redundant calculations. In contrast, the current solution optimizes this process by using a 1D painted array to track which sections are already painted, avoiding redundant checks. This efficiency is reflected in the overall time complexity of n plus L. The justification for this complexity is straightforward. The first step, finding the maximum endpoint, takes n, while the second step, marking painted sections, is proportional to the total length of painted regions, which is L. Adding these together results in n plus L. For space complexity, the painted array contributes m space, while the result list adds n, giving us a total of m plus n. Finally, let's consider the best, average, and worst cases for time complexity. In the best case, where intervals are disjoint and their total length L is small, the time complexity is n. In the average case, the complexity is n plus L, where L depends on the overlap between intervals. In the worst case, if all intervals overlap heavily and cover a large range, the solution still operates efficiently with a time complexity of n plus L. Regardless of the scenario, the optimized approach ensures that redundant calculations are minimized, making it significantly faster and more space-efficient compared to a brute force solution. When solving this problem, there are several common mistakes to watch out for. One of the most frequent errors is failing to account for overlapping intervals. For example, if you have two intervals like 1, 5, and 3, 7, the section where they overlap, 3, 5, might get counted more than once in a naive implementation. This leads to incorrect calculations of the total painted area. Another issue is using inefficient methods to update the painted state. If you perform an n operation for each interval, you end up with an n squared time complexity, which is impractical for large inputs. Instead, you should aim for more efficient techniques, such as prefix sums or segment trees. Additionally, misinterpreting the bounds of intervals is another common pitfall. Since intervals are often given in an inclusive-exclusive format, start to end, forgetting to exclude the end value can introduce off-by-one errors. Lastly, some solutions unnecessarily complicate edge case handling, such as 4, 0, 0, or fully disjoint intervals. A well-designed general solution should handle these cases without extra conditions. It's also important to consider constraints when designing your solution. For example, if the range of values is very large, such as up to 10⁻⁹, using a straightforward painted array to represent the entire range becomes impractical due to memory limitations. In such cases, you should use compressed representations or data structures that dynamically adjust to the active range. From an interview perspective, this problem often tests your ability to manage intervals efficiently. Techniques like processing intervals in sorted order with a greedy algorithm, using advanced data structures such as segment trees or binary index trees, or applying sweepline algorithms are commonly evaluated. Interviewers are particularly interested in how you scale your solution. While a naive n squared, or n asterisk k, approach might work for small inputs, you should aim for more optimized solutions like n log n, or even n, by leveraging efficient data structures. If you're feeling stuck, focus on clarifying assumptions, such as the bounds or behavior of overlapping intervals, and explore alternative strategies like greedy methods or divide and conquer. Even if your first solution isn't perfect, demonstrating a structured thought process is key. In interviews, you might encounter follow-up questions that test the adaptability of your solution. For instance, you could be asked how your approach would handle dynamic updates, such as adding or removing intervals over time. Another common variation is adapting the solution for distributed systems or parallel computation, which introduces additional challenges in synchronizing updates and ensuring consistency. This problem also relates to several other interval-based problems on LeetCode. For example, LeetCode 56, merge intervals, focuses on combining overlapping intervals, which is a fundamental skill for managing ranges. LeetCode 1288, remove covered intervals, asks you to identify and discard redundant intervals, further testing your understanding of range management. LeetCode 218, the skyline problem, involves handling overlapping intervals in a two-dimensional space, often using sweepline algorithms. Finally, LeetCode 715, range module, is a more advanced problem that involves dynamically adding, removing, and querying intervals, making it especially relevant for solutions requiring flexibility. There are several alternative approaches you can consider for solving this problem. One is the prefix sum approach, where you mark the start and end points of intervals in an auxiliary array. By computing the prefix sum, you can avoid iterating over ranges directly, achieving a time complexity of O, n plus k, where n is the number of intervals and k is the compressed range size. Another powerful method is to use a segment tree or binary index tree. These data structures allow efficient dynamic updates and range queries, reducing the complexity of operations to O log n. While they can be more complex to implement, they are highly effective for problems involving frequent updates. The sweepline algorithm is another strong option. By sorting intervals based on their start points and using a priority queue to manage endpoints, you can efficiently handle interval overlaps with a time complexity of O, n log n. Finally, a simpler but less flexible approach is greedy sorting, where you sort intervals by their start times and process them sequentially. While this works well for static problems, it may not be suitable for dynamic updates. Each of these methods has its strengths and is worth understanding to apply effectively in different scenarios. Great job! In this session, we tackled problem number 2158 and explored how to calculate the amount of new area painted each day. We discussed the brute force solution, identified its inefficiencies, and worked towards a more optimized approach. Remember, understanding interval problems and using the right data structures are key takeaways from this session. Thanks for watching, and don't forget to like and subscribe for more coding tips and solutions. See you next time. That's the end of this tutorial. I hope you found this explanation helpful for understanding the solution to this LeetCode problem. If you enjoyed this content, please consider subscribing to the channel for more coding tutorials and solutions. Feel free to leave a like if this video helped you, and don't hesitate to comment with any questions you might have. Thanks for watching, and happy coding!